now right triangle trigonometry, section 5.4. We will start with this approach to the trigonometric functions because it's the easiest. It's not following the order in which it's presented in the textbook, but I believe that this is the best thing to do. First, we start with the easiest approach. Then tomorrow we will go over trigonometric functions any angle, and then the unit circle at the end, which is the most sophisticated approach for trigonometry, right? Yeah. So let's try to start with right triangles first, the small angles. Given a right triangle, meaning this guy 90 degrees, right? You will see always this corner, right? Then we can always think of an angle between 0 degrees and 90 degrees here. Okay, let's call it theta. And also we can see three sides for this right triangle, right? The longest, the one opposed the 90-degree angle, the corner, is called the hypotenuse. The opposite angle is the opposite side with respect to this angle is called the side opposite theta, and the adjacent side is called side adjacent to theta, right? So adjacent, opposite, hypotenuse. Now shorthand for these guys, for this we will write just HYP. For this side adjacent to theta, just ADJ. And for this guy, we'll just write OPP, opposite. The angle is a small angle. It's between 0 degrees and 90 degrees. These small angles, the one within these two values, are called acute angles. Okay, try to remember this for your homework. Acute angle. Acute angle is any angle between 0 degrees and 90 degrees. Okay, now looking at these three lengths, we can form 6 possible ratios, right? 6 possible ratios. The first ratio is called sine. Sine of theta is defined as opposite over hypotenuse, okay? Opposite over hypotenuse. So we're going to write here, opposite over hypotenuse. That's called sine. The second ratio between the side lengths is called cosine. Cosine of theta is defined as adjacent over hypotenuse. Great. And the third ratio is called tangent. Tangent of theta is defined as opposite over adjacent. Opposite over adjacent, okay? Now, there are 3 more, but these sort of come for free. How? You just flip these guys to get these other guys, right? For example, if you flip sine, you're gonna get cosecant. Cosecant is defined to be hypotenuse, right? Over opposite, okay? Secant is what you get when you flip cosine. So hypotenuse up here, adjacent down here. So hypotenuse over adjacent. And cotangent is what you get when you flip tangent. Adjacent here over opposite. Okay. These 3 are reciprocals of these 3, right? Reciprocals. Now, a mnemonic device to remember these definitions in case you have a hard time memorizing these definitions is this. If you memorize the word SOHCAHTOA, then this part, so, tells you that sine is equal to opposite over hypotenuse. This other part, the CA, tells you that cosine is equal to adjacent over hypotenuse. And the TOA tells you that tangent is equal to opposite over adjacent, okay? If in case you want to use this mnemonic device, go ahead and use it. These are the definitions. Now, what kind of questions are related to this part? Well, first form is this. Example 1, given a right triangle whose hypotenuse is 25, adjacent side 7 in length, right? Angle theta here. Find the values of the 6 trigonometric functions of theta. all the trigonometric functions of theta. Let's do it together. All right, so solutions. First, complete the triangle. Complete the triangle. What do you mean, Professor, by complete the triangle? Well, find the side lengths for this triangle, all of them, right? This one is missing. Find it using the theorem of Pythagoras. So using the theorem of Pythagoras. All right, let's do it together. So we have this guy is 25 in length, right? Oh, this one, right? 7. And we'll take this here. We don't have this length, but let's call it A, small a. Use the theorem of Pythagoras, which says that the sum of the squares of the legs, right, equal to the square of the hypotenuse, right? From there, this is 49. 25 squared, 625, right? You can check that with your calculator. Subtracting 49 both sides, a squared equal, this difference is equal to 576. And once you take the square root of 576, what you are gonna get here for A, for the side length, what I was missing is 24, right? Professor, how you did this in the calculator? Well, I will show you now. A square root of 576, this is this. A square root of 576, 24, right? That's why you wrote here. Very good. Once you find this guy, quickly write it here, 24, and then we have completed the triangle, right? You can see. Now that we have completed a triangle, we are ready to compute our ratios, right? Starting with sine. Sine, remember, according to SOHCAHTOA, sine, opposite over hypotenuse, right? Opposite, this guy 24, hypotenuse 25. So there where I got sine, right? Got sine. Cosine of theta, according to this K, adjacent, which is this guy, right? 7 over hypotenuse 25, right? Yeah, there you go. And tangent of theta, following TOA, opposite over adjacent, so opposite 24, adjacent 7, right? This is the tangent. Now, what about the other three trigonometric functions, Professor? Cosecant of theta is just the reciprocal of this, right? This up, this down. So you flip sine, you get sort of for free cosecant, right? This is. Secant is what we get when we flip cosine. So 25 up, 7 down. There is secant. And cotangent is what we get when we flip tangent. 7 up here, 24 down. So there we have the 6 trigonometric functions. So we are done, right? We're done. Now, let me give you something to work on quickly, and then we will do this special case. Can you try to do what I did with this? I'm going to give you a hint. Sine here is opposite over hypotenuse, right? So make up a triangle where the opposite is 5 and your hypotenuse is 13, and follow what I did in the example, right? Try to complete the triangle first, and then you have to use the definitions, right? So complete the triangle first. We don't have this base, call it B. And using the theorem of Pythagoras, find B, and then you write out all the definitions following SOHCAHTOA, right? TOA. I see students are readily sending answers. 13 squared, B squared plus 5 squared. That's how we want to find B, right? Very good, guys. Very good, very good. Jing. Very good, Jing. Excellent. Yeah, keep working, guys. Yeah, very good, Jing, right? Yeah, we find B here. This 13 squared is 169. 5 squared is 25. Subtracting from both sides, the 25 will get 144 equal B squared. So B is square root of 144, which is just 12, right? 12. Excellent. This be 12. Very good. Now, once you complete your triangle, you go ahead and follow the definitions given by the SOHCAHTOA, right? Sine is opposite over hypotenuse, right? Opposite 5 over hypotenuse 13, right? There we go, sine. And then cosine is opposite over adjacent, right? And tangent, right? Tangent, which they are asking you to get, right? They're not asking you really to get everything, just tangent, right? Tangent will be opposite 5 over adjacent. This was 13, sorry, this is hypotenuse 13. 5 over adjacent 12, right? So very good. And this is this. Now, what to do when they give you radicals? Radicals, like in here, right? Say, Professor, could you explain that? It's tricky. So I will give you an example here first. Let's do it here. What to do when they give you radicals? For example, this, right? Tangent of theta is square root of 3 over 2, for instance. How to deal with this? They want cosine. All right, so as I did before, right? To solve this, think of this, right? Tangent, according to SOHCAHTOA, is opposite over adjacent, right? So this should be considered to be the opposite. And this should be considered to be the adjacent, right? When we make up the triangle. So when you make up the triangle, theta is here. Adjacent should be 2 opposite the square root of 3. So opposite the square root of 3 here, adjacent 2. This time, the hypotenuse is missing, right, in length. So see, so no problem because we have the theorem of Pythagoras that's going to help us to find this side length C, right? C squared will be equal to what? 2 squared 4. The square root of 3 is canceled with the square, right? This is just 3. And 4 plus 3, believe it or not, guys, is just 7. So since it's just 7, then it means that when you take square roots in both sides, C will be equal to the square root of 7, right? The square root of 7. Yeah, this cancels with this. Very good. So this square root of 7 is what you should write here quickly. Equal square root of 7. Great. We completed the triangle, right? Now we are ready to get all trigonometry functions, but in particular, we need just this, right? Cosine. So what is cosine of theta? Remember from SOHCAHTOA, from this part, acá says cosine adjacent over hypotenuse. Adjacent is 2. Hypotenuse is the square root of 7. This should be the answer, right? But however, often mathematicians may want you to rationalize this, right? Rationalize. Rationalizing this, remember the technique to rationalize this is multiply top and bottom by the square root that appears here on the denominator, right? If you do that, your answer rationalized should be equal to this 2 times the square root of 7, and over here the square root of 7 times the square root of 7 is the square root of 49, but that is just the number 7, right? This is the answer rationalized in exact form. All right, guys, so with this, let's go back to the worksheet and let's try to do this guy. I think he's here. I think we can do this guy now. Can you try this? I will give you some hints. Let's try this out. Try to figure out what is sine of theta. For that, make up a triangle. Since we are dealing with the small angles, acute angles, we can always put our angles inside a right triangle. But this, from SOHCAHTOA, cotangent is the reciprocal of tangent, right? Tangent is opposite over adjacent. So this should be adjacent over opposite, right? So adjacent should be a square root of 3 and opposite should be 3. So try to work with this triangle, right? There, apply the theorem of Pythagoras and try to see if you can find it. And then once you complete the triangle, we can go ahead and figure out what is sine of theta after rationalizing, right? Jingjing. Let me check, Jingjing. Number 2. I think it needs a little adjustment, Jingjing. But check. Number 2. Yeah, it's tricky, very tricky. Probably we can do it together, right? All right, let me show you this, guys, so we can move on. From the theorem of Pythagoras, we're gonna get this. The square root cancels with this exponent 2. This is 3 plus 3 squared, 9. C squared equals 12. But then C will be equal to the square root of 12. But this can be simplified as a square root of 4 times 3. The square root of 4 is 2. The square root of 3 stays there, right? This guy. Now, they are asking us to compute sine of theta, right? Sine of theta. But what is sine of theta according to SOHCAHTOA? So it says opposite over hypotenuse, right? Opposite over hypotenuse. Opposite is this, 3. Hypotenuse is C, but hypotenuse is just this guy, right? 2 is square root of 3. So over 2 is square root of 3. Here is the tricky part, guys. Here we have to rationalize. Rationalize. How do we rationalize, Professor? Well, you multiply by a square root of 3 top and bottom, right? I see some corrections there. Let me check. Times the square root of 3 here, times the square root of 3 here. Yeah, very good, Jingjing. Yeah, fix it. Yeah, great. So this will be sine of theta equal, they're asking for sine, right? Very good, very good. 3 times square root of 3 over here, 2 times. What is this? This is a square root of 3 times square root of 3 is square root of 9, right? But the square root of 9, isn't it just 3, right? It's a very tricky problem, yeah, 3. And in turn, this number 3 cancels with this number 2 on the top. So believe it or not, guys, sine of theta here equal a square root of 3 over 2. Okay, so this guy. Very tricky problem. Check it out at home. Keep it in mind. All right, great. So we have done this. Now let's talk about these properties. But before, I should show you how to compute sine, cosine, tangent of special angles, such as 45 degrees and 30 degrees and 60 degrees. I will show you. 45 degrees, when you convert it to radians and simplify, is pi over 4 radians. That's why you see this next to this guy, okay? This in radians, this in degree. But how mathematicians figure out sine, cosine, tangent, cosecant, secant, and cotangent of 45 degrees? Here is the explanation. Start with a square, right? Square that you split into this way. If you split the square into 2 regions via this diagonal, right? Since the corner is 90 degrees, the half of 90 degrees is 45 degrees, right? So this angle should be 45 degrees, how this angle appears there. Now, suppose this is one unit, right? Does not really matter what measurement you take there, because these trigonometric functions, they are all ratios, right? So let's say the length of the side of this square is 1 here, right? Now I want you to focus all your attention to this part, to this triangle, this right triangle, right there. In this right triangle, we can apply our knowledge of trigonometric functions, okay? This right triangle. So, but before, as we did before, right? We don't have this length. Let's find it before, right? Let's complete the triangle before. So using the theorem of Pythagoras, c squared is going to be equal to 1 squared plus 1 squared, c squared equal 1 plus 1, c squared equal 2, and c, after taking the square roots on both sides, is square root of 2, right? So this guy is square root of 2. We found it here. So now that we found it, let's compute sine of 45 degrees. Sine of 45 degrees, according to SOHCAHTOA, remember, is what? Opposite over hypotenuse. Opposite is 1. Hypotenuse is a square root of 2. 1 over square root of 2, right? But rationalizing this, multiplying by a square root of 2 here, by square root of 2 here, we get this rationalized. A square root of 2 over 2. And I want you to remember this, guys. A square root of 2 over 2, they define sine of 45 degrees always. All right, next. What about cosine? Cosine will be, according to this K, adjacent over hypotenuse, so 1 over a square root of 2. But following the same rationalization process, right, we will end up with this rationalized result, right? The square root of 2 over 2, right? Great. Tangent, opposite over adjacent. Opposite is 1, adjacent is 1, so 1 over 1. Look at this surprising result, 1, right? 1. So I want you to be aware, guys, that sine of 45 degrees is square root of 2 over 2. Cosine of 45 degrees is square root of 2 over 2. Tangent of 45 degrees, 1. For these guys, they come for free once we flip these guys, right? If we flip sine in this form, right, this will be a square root of 2 over 1, which is a square root of 2, right? If we flip cosine to get secant, if we flip this guy, this will be a square root of 2 over 1, but that is just a square root of 2, right? And if we flip 1 over 1, we end up with 1 over 1 again. So tangent and cotangent for 45 degrees, the same, right? Try to remember these results, guys, will help you later. Okay, next, how mathematicians figure out the trigonometric function of 30 degrees and 60 degrees. They start now with an equilateral triangle, right? Whose side length is 2. 2 here, 2 here, 2 here. Split your equilateral triangle, so you will get this to be 1, this 1. Now, since it's an equilateral triangle, this guy should be 60 degrees, right? And since you are splitting the angle here, 60 degrees divided by 2, 30 degrees, right? So I want you to focus now on this triangle, right? This is showing the two angles we are after, 60 degrees and 30 degrees. So let's use this triangle to compute the trigonometric function of 60 degrees and 30 degrees. But before we start, let's complete this triangle. We don't have this height, let's call it B. Using the theorem of Pythagoras, that B can be found. B squared plus 1 squared equal 2 squared. Doing the math here is equal to 4. B squared equal 3. B equal square root of 3, right? We found it. So this is equal to square root of 3. Now use SOHCAHTOA, find all the trigonometric functions, right? And flipping them, you can get this other guy, right? Sine of 60, for example. Sine of 60 will be opposite, right? Square root of 3 over hypotenuse 2, right? Cosine of 60 degrees, 1 over 2. Adjacent over hypotenuse. Tangent of 60 degrees, opposite the square root of 3 over adjacent 1 square root of 3, right? Now, flipping these guys, you can get 2 over square root of 3 here, but rationalizing this, you get 2 square root of 3 over 3, right? Final result. Secant of 60 degrees, flip this, 2 over 1, but 2 over 1 is just 2. Cotangent, flip tangent, 1 over square root of 3, but 1 over square root of 3, after you rationalize the denominator, right, you will end up with square root of 3 over 3, right? So try to remember those results, guys. Similarly, for sine of 30, look opposite 1 divided by hypotenuse for sine gives you 1/2. Cosine adjacent square root of 2 over 2. And tangent opposite 1 over hypotenuse square root of 3, rationalizing, you get the square root of 3 over 3. Professor, these numbers look familiar to me. Yeah, 1/2 is here. The square root of 3 over 2 is here. And this guy flip is here, right? So the reason is 60 and 90 degrees are complementary angles, right? With respect to each other. So the trigonometric functions are very similar. They're kind of, they appear in different places, right? So sine of 60 is cosine of 30, cosine of 30, sine of 60, vice versa, right? So flipping these guys, you will get here 2. Flipping the guy 2 over square root of 3, but rationalizing 2 square root of 3 over 3. And cotangent, flipping this version of tangent, this is just square root of 3. Try to remember this, guys, because we're going to need this for your homework when they ask you to find the trigonometric functions of 30 and 60 in exact form. But now, how this is going to be tested for us? Here is an example that you will have to take a look at in your homework. In the figure below, find the values of B and C. Look, B and C, they're giving you this length 5 and this pi over 6. Notice that pi over 6 in degrees is just this angle. Pi cancels, 6 into 180, 30 degrees, right? 30 degrees. So this equal 30 degrees, right? So they are basically asking you to figure out what is C and B once this is 30 degrees. But the good news is that we know the trigonometric functions of 30 degrees, right? So use that fact, right? We know all the trigonometric functions of 30 degrees, they are here, right? So you are trying to find the value of B, for example, right? So use a trigonometric function that is going to relate 5 with b. And what would be that according to SOHCAHTOA? Well, I want the opposite and the adjacent to be related. I should use tangent, right? So tangent of pi over 6 equals what? Opposite 5 over adjacent b, right? But at the same time, since this guy, pi over 6, is 30 degrees, right? I know that tangent of 30 degrees, according to my calculations here, is a square root of 3 over 6, right? The square root of 3 over 3 is 6 is tangent of pi over 6, right? So from there, solve for b, right? So this guy, if you cross multiply this equation, you get b times the square root of 3 equal 5 times 3, 15, right? 5 times 3, 15. Dividing both sides by a square root of 3, we get this. Rationalizing, you should get the result, right? B equal 15 square root of 3 over 3, which ends up being just 5 times the square root of 3. This is B. Similarly, in order to find C, you can use, for example, something that relates the opposite with the hypotenuse, sine, right? Sine. Use a different color here. Sine of pi over 6, opposite 5 over hypotenuse C. But at the same time, you know that this 5 over C, sine of pi over 6, sine of 30 degrees is 1/2, right? Professor, how do you know sine of 30 degrees is 1/2? Is here. Sine of 30 is 1/2. So just make them equal, cross multiply, and you should get your answer from there. C times 1 is C, 5 times 2 is 10. So there you go, C equal 10, right? We were able to find both. Very good, guys. Now let me go to probably to the worksheet and let you work on. But I think in the worksheet we need identities now. Yeah, I see. Yeah, identities. But in order to, identities now. Yeah, let's talk about identities first. Turns out there are relationships between trigonometric functions. Mathematicians have organized these three relationships. They call them identities in three groups. The first group, the easiest, is this: reciprocal identities. They just say that sine is the reciprocal of cosecant, so therefore sine should be 1 over cosecant, right? Similarly, cosine, reciprocal of secant, so cosine 1 over secant. Tangent is gotten by cotangent, sorry, is gotten by flipping tangent, so cotangent 1 over cotangent. And similarly, cosecant 1 over sine, secant 1 over cosine, cotangent 1 over tangent, because they are reciprocals of each other, right? Yeah, this is kind of obvious. Now, second group, quotient identities. Quotient identities deal with this: tangent equals sine over cosine, cotangent cosine over sine. Professor, how come tangent sine over cosine? Well, notice, I'm going to do this in the side. Tangent of theta is what? Is, according to SOHCAHTOA, opposite over adjacent, right? But what if you divide both this guy and this guy by hypotenuse? The value of the fraction is not going to change, but this will allow you to say that tangent is the same as opposite over hypotenuse over adjacent over hypotenuse. But applying the trigonometric functions, this opposite over hypotenuse is sine. This adjacent over hypotenuse cosine, and there you have your identity, right? Yeah, they're not hard to prove, but the idea is to present them now and learn how to use them now, right, to simplify trigonometric expressions. So quotient identities: tangent equals sine over cosine, cotangent cosine over sine. The last group is called Pythagorean identities. And they say that if you square sine, you square cosine, you add them, you will get always 1. And again, this is not hard to believe, guys, or to prove because of this. Sine of theta square cosine of theta square equal 1. How this could be true? Well, sine is opposite over hypotenuse plus cosine adjacent over hypotenuse. If you square them, right? Let's say you don't believe this. Opposite square plus adjacent square all over hypotenuse square, right? Opposite square by adjacent square is hypotenuse square, right? So it checks. This is hypotenuse square over hypotenuse square here equal 1. Checks. So this is good. And this is a derivation of this once you divide both sides of your equation by the sine square first to get this, right? This 1, this tangent square, and then secant square. Cosine square first, and then sine square. You get these 2. So we have all the properties, identities, right? Justified. It's not hard to prove. All right, but now what is important at this level, guys, as I explained, is that how to use these properties to simplify trigonometric expressions such as this, for example, right? How to simplify this using our properties. Well, one thing we can do there is this. We can apply our distributive property, right? So we get cotangent of theta times sine of theta plus cotangent of theta times tangent of theta minus 1, right? But what is cotangent of theta times sine of theta? Cotangent of theta, according to our quotient identity, should be cosine of theta over sine of theta times sine of theta here, plus cotangent of theta is cosine of theta over sine of theta. According to our quotient identity, this tangent is sine of theta over cosine of theta, right? Minus 1. This guy cancels with this. Cosine of theta stays. Plus cosine of theta cancels with cosine of theta. Sine of theta cancels with sine of theta. The result of all this is just 1 minus 1 here. Notice after canceling these 2, it got simplified to cosine of theta, right? So this is the idea, guys, to use these properties to show that these big expressions can be simplified into small expressions such as this, right? Cosine of theta, for example, here. Yeah, great. So now let's go for the applications to our worksheets. You will see that they are not difficult. So for example, can you try this similar to the one that I just did, number 3? I will give you the hint, some properties that eventually you should memorize. They will simplify your life tremendously, but if not, you can derive it, right? A hint, use that fact that tangent of theta is equal to sine of theta over cosine of theta, right? That's and the fact that cotangent of theta, do this, right, is equal to cosine of theta over sine of theta. Use these 2 facts. It's a quotient identity, right? And of course, use the distributive property. Can you try this, guys? Try, please. Simplify. Okay, so let me see. Let me give you another hint. Tangent of theta must multiply cotangent of theta minus tangent of theta here, multiplying cosine of theta, right? And then use these two. Write everything in terms of sine and cosines, and it should be okay. All right, let's do it together so we can move on. A tangent, remember, based on the quotient identity, is equal to sine of theta over cosine of theta. Cotangent is cosine of theta over sine of theta, right? Minus tangent, sine of theta over cosine of theta. Cosine is just cosine. Simplifying, look, cosine cancels with cosine, sine cancels with sine. This is just 1. Minus cosine cancels with cosine. 1 minus sine of theta is the simplified version of this expression, right? So this guy. Okay, guys, another one here. Let's probably do this one and then we'll move on to the next. Try to do this. Tangent of theta divided by secant of theta. Hint, tangent of theta is equal to sine of theta over cosine of theta. And secant of theta, according to the reciprocal identities, 1 over cosine of theta, right? Use these two. Divide this here, right? Sine of theta, cosine of theta. And here 1 over cosine of theta. Remember, to divide by a fraction, flip the fraction and multiply, right? Remember? Yeah, try that. Okay, let's show this. Keep the numerator as it is, sine of theta over cosine of theta. Multiply by the reciprocal of the denominator, cosine of theta over 1. Notice cosine and cosine cancels. Sine of theta over 1 is just sine of theta, right? So this is this guy. Now let's talk about how to use the calculator in case the angles are not special, are not 45 degrees, are not 60 degrees. Let me explain 9/9 to you, and then I will ask you to do this one, okay? How to compute sine of 61 degrees and approximate it to 2 decimal places. Well, pretty straightforward. You go to your calculator and you look for the function sine. Function sine is here, 61 degrees here. Okay, now this is what you get, right? But now make sure that you are working with degrees, because if you click in here, then you will be working on radians, right? Degrees. Whatever the calculator you are using, make sure you are working in degrees, right? Degrees, radians. 0.87. 0.87 once you round it to 2 decimal places, right? Great. Can you try this? Jing, excellent, number 10. Yeah, very good, right? Yeah, again, you just go to the calculator, cosine now. Where is cosine? Either you write COS with a keyboard, or you look for the function cosine is here, 62 degrees. And that's the answer, right? 0.46, rounded to 2 decimal places, 0.47. 0.47, right? This guy. Mhm. Excellent, excellent. Now, what to do when the question is in degree, not in degrees, but in radians? So this, right? What about this? Can you, let me show you this, right? Quickly. Cosine of 5 pi over 12. Radians. Professor, how do you know that it's radians? Well, because there is a mathematical agreement, right? If you don't see any units next to the angle, and especially if you see pi there, right? It has to be radians, right? Yeah, what is this? Well, you go to the calculator, but you have to be careful, guys. You go do this, 5 pi over 12, right? But you're taking cosine, right? So this is from the start. Cosine function, cosine of 5 pi over 12. And by default, our scientific calculator will give the answer in degrees, but this is not it. You have to go to radians. Radians 0.258, it will be 0.26, right? Again, radians. Don't get this, it's degrees. In degrees is in radians, so 0.26. So we are talking about this guy, right? Okay. So now let's see some application problems. Let me show you this one. Yeah, this one's better. This probably is easier. This one is good. What to do if they ask you to compute, for example, the length of this river here? It says a conservation officer needs to know the width of a river in order to set instruments correctly for study of pollutants in the river. From point A, the conservation officer walks this point, right, 95 feet downstream, and sights point B on the opposite bank to determine that the angle is 30 degrees here. How wide is the river? How wide is the river, right? So basically we focus our attention to this, right? This triangle. We have the angle here 30 degrees, right? We need this length, right? We don't have it. Let's represent it by B, okay? But we want a trigonometric function that will relate B with this 95 feet that we have. So based on SOHCAHTOA, anyone could tell me what trigonometric function should be convenient for this problem? Is it sine, cosine, tangent? Jing, you made my day. Tangent, right? Tangent, excellent. Why tangent? Because tangent relates opposite, which is this guy, right? Opposite, and adjacent, which is this, right? I don't have the hypotenuse, so I cannot work with sine because sine is opposite of hypotenuse, cosine adjacent or hypotenuse because I don't have the hypotenuse. So conveniently choose the trigonometric function. In this case, happen to be tangent, right? Tangent of 30 degrees equal to B over 95 feet, right? 95 feet. Now, in this problem, you can see the answers are just numbers, right? You don't see radicals, so there is no need to show or to utilize this in exact form. Use the calculator, right? Use the calculator. So basically solve this for B, and that is gonna be gotten by multiplying both sides of this equation by 95, right? To eliminate the denominator, right? So here we will get that B, what we are looking for, should be equal to 95 multiplied by the tangent of 30 degrees. We want this as a number, right? So let's just put it in our calculator and round it, right, if needed. 95 multiplied by tangent function, we go to tangent of 30 degrees. That gives us 54.85, right? But you see that all the numbers are whole numbers. So let's round it to the nearest whole number. Rounded to the nearest whole number, this would be 55, right? 55. Notice I am using degrees because this is in degrees, right? So be careful there. So 55. In the end, you can attach the units, in this case, feet, right? 55 feet. talking about this side, right? Excellent, excellent. Now to finish, let me ask you to do this problem, which is similar. Just find the height of a pine. I'm gonna do the drawing here for you. Find the height of a pine tree that casts a 48 foot here, shadow, on the ground, assuming that the angle of elevation from the point on the ground at the tip of the shadow to the sun is 63 degrees, right? 63 degrees here, right? The sun somewhere there. Yeah, so round your answer to the nearest foot, right? So basically we're asking for this height, which we're gonna represent with B. Can you find it? Following kind of what I did with the previous problem. For your reference of Gatoa here. And choose again a well-chosen trigonometric function. It could be sine, cosine of tangent, and just follow the algebra and you should be okay. Ying, excellent, very good, huh? Very good, excellent. Yeah, notice that if you focus your attention to this triangle, right, formed by the pine growing vertically, right? Focus your attention to this triangle. Not hard to see that there in this triangle, a good choice for a trigonometric function to work with should be tangent, right? Tangent given by this TOA, because tangent of this angle 63 degrees relates the height B opposite, right? And the adjacent 48 feet, right? From there, you can multiply both sides by 48, right? Eliminate these two guys, and B should be equal to 48 multiplied by tangent of 63 degrees, right? So B should be equal to approximately equal to 48 multiplied by function here, tangent here, 63, 94.21, rounded to the nearest whole number, 94, right? 94 feet. Very good. Excellent, guys. This is this, right? Yeah, excellent. Okay, guys.